Hello, stat students. So last time we learned about discrete random variables and continuous random variables. You learned how to calculate the mean or the expected value and the standard deviation of a random variable. Today we're going to continue working with random variables. We're going to talk about transformations of random variables. Going back to chapter 2, we learned that when we added or subtracted a constant a to each observation, what it did was it added a to the individual values and mean, but it did not change the shape and it does not do anything to the spread. So, for instance, if we had a distribution, if I can get it to work. Okay, there we go. So, if we had a distribution, all it did, adding a constant, adding or subtracting, shifted it right or left, but it did not change the shape. Meaning, if the shape was right skewed, then it would stay right skewed, and it does not do anything to the spread because the difference, the deviation from the mean, is still going to be the same. As far as multiplying or dividing each observation by a constant, let's call that constant b, what it does is it scales, it multiplies or divides by b to each individual value and to the center, to the mean, and it multiplies or divides by b to the spread. So it does affect the spread because it's scaled by b as well, times b, or divide by b, but it does not change the shape. So again, the shape doesn't change, the shape stays the same. We are going to see if the same rules from chapter 2 will apply to random variables. So let's look at a problem. Pete's Jeep Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Define X as the number of passengers on a randomly selected day. So the top row is passengers anywhere from 2 to 6, and the bottom rows are the probabilities for having that many passengers on that trip. What I did was I entered list 1. You could do this by hand. It doesn't take very long. It's the standard deviation that takes a while. So if you didn't have a calculator and I just told you to find the expected value or the mean, you would do 2 times 0.15 plus 3 times 0.25 plus 4 times 0.35, so on. Add it all together, and it gives you 3.75 people. But if you had a calculator, of course, you want to do that. So enter your passengers in list 1 and your probabilities in list 2, and then you're going to do go to stat and go to calculate, and you're going to do a one variable statistics. And you want to put L2 in your frequency. And the mean and the standard deviation will be given to you. And the standard deviation is 1.09 people. And this is just the original distribution, so we haven't even done a transformation yet. If you look at the shape of the distribution, notice you see there, you just have a shape. You don't have to describe it, but you know what that shape looks like, so we can do the actual transformation. So I'm going to keep that up. I know yours is on a different page. I'm sorry about that. And then I have it to where you can see both of them at the same time. So here's the transformation. Pete charges $150 per passenger. The random variable C describes the amount Pete collects on a randomly selected day. So here we have a new variable C. So the top row is the amount collected. So for 2 passengers, that'd be 2 times 150. So that'd be 300, and then so on. 3 passengers, 3 times 150. So there's where the top row comes from. The probabilities are still the same. That's not going to change. And you do the same thing to find the mean and standard deviation. You would enter this in list 1, the amounts collected, and then the probabilities in list 2, and you would do the one variable stats again. Just need to remember that when you're dealing with probabilities, you want to use the frequency and use the L2. Normally, when we're using just regular one variable stats, we just have the list one that we're interested in. So the mean is $562.50, and the standard deviation is $163.46. And there's the shape. So now we're going to compare the shape, center, and spread of the two probability distributions that we've done. So if you look at the shape's the same. I mean, it hasn't changed any. So the shapes are the same. The mean, so here's what we're interested in. What happens to the means? The means are definitely not the same. You have 3.75, then you have 562.50. But how did they change? According to what we read, is it indeed going to be multiplied by a specific value? And that specific value would have to be 150. So what I did was I took the 3.75, which was the mean of the first distribution, and multiplied by 150, and I got $562.50. So the mean of the transform distribution, so that would be, the mean of C, the amount collected, is equal to the mean of the original distribution, the mean of X, times 150, or 150 times the mean of X. And that's how we got $562.50. For the standard deviation, I took the standard deviation of X, which is 1.09, and I multiplied it by 150 to see if I would get $163.46. And I got $163.50, I believe. But that's close enough because remember, we rounded the 1.09 standard deviation when we're using our calculator. So that's a rounding error, so it's close enough. So the standard deviation of the transform variable, so C, is equal to the standard deviation of the original distribution times 150. So 150 times 1.09 gave me 163.46, close enough anyway. So the transformation rules did apply. Oops. This section is not too bad. So there's where the multiplication comes in. So now the rules for multiplying or dividing a constant for random variables. Multiplying or dividing each value of a random variable by a number b multiplies or divides the location, or so the individual values, and the center by b. So it does scale it by b. It multiplies or divides the spread by the absolute value of b. And I put absolute value because distance is not negative, and so therefore the absolute value b. It does not change the shape. And then there's a note here at the bottom. Multiplying a random variable by a constant b multiplies the variance by b squared, since variance is standard deviation squared. So going back to what variance actually is, variance is equal to the standard deviation squared. So if we have the if we multiply the standard deviation times b and you square it, then that's how you get the b squared. So multiplying a random variable by constant b multiplies the variance by b squared. There you go. All right, let's do some more sample problems. This one is called El Dorado Community College. El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 units, so that's credits. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester has the following probability distribution. So the top row is 12 units all the way up to 18 units, and then the probabilities listed below. What is the mean and standard deviation of the distribution? So again, put this in list one. You should always try doing one of these later just to make sure that you get the same answers. So list one, list two, then the one variable stats, and then put list 1, list 2 as your frequency. And you would see that in your prompt if you have a newer calculator. I just don't know what calculator you're using. What is the mean and standard deviation of the distribution? So putting all that in, it'll give you the mean, so the expected value of that random variable x is 14.65 units, and the standard deviation of x is 2.06 units. So that's the original distribution. At El Dorado Community College, the tuition for full-time students is $50 per unit. That is, if T is equal to the tuition charge for a randomly selected full-time student, then T will be equal to 50 times X, so X being the number of units. So 50 times, if a person took 12 units, would be $600. If a person took 13, it'd be 50 times 13, which would be $650, and so on. So there's your equation right here. What is the mean and standard deviation of the transform distribution? So we said that we would multiply the original distribution by 50. So the mean of the tuition is equal to 50 times mean of x. So that would be 50 times 14.65. So the mean of T is equal to $732.50. And then for the standard deviation, the scaling does affect standard deviation. So you would multiply 50 times the original standard deviation. So it'd be 50 times 2.06. And that is 103. What would the distribution look like? Well, if a person took 12 credits, it'd be $600, $650, $700, $750, $800, $850, $900. Probabilities don't change. All right, let's go back to Pete's Jeep tours again. So we define C as the amount of money Pete collects on a randomly selected day. So just going back and just putting in the answers we already got. This one was $562.50 for the mean amount collected, and the standard deviation was $163.46. So list 1, list 2. And the probabilities stay the same. Here's another transformation. It costs Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable V will describe the profit Pete makes on a randomly selected day. So the profit is in the top row, and so all I did was I just deducted $100 from the amount collected. So $300, because it's $150 per passenger, be $300, and you deduct a $100 for each trip. So the mean is, so if you put this in list 1 and this in list 2 and use your one variable stats, you end up getting the mean is $462.50, and the standard deviation would be $163.46. And now we're going to compare the shape, center, and spread of the two distributions, the original one and the transformed one. So notice the shapes are the same. Okay. The profit, so let's just call this, okay, so the mean, probably didn't use P for profit because little p for probability. So the mean of the profit is equal to the mean of the amount collected minus $100, and the standard deviation of the profit is equal to the standard deviation of the amount collected, because that did not change. If you look at the top distribution, it was still 163.46, and the bottom one is 163.46. So the main thing to realize in this one is standard deviation is unaffected by adding or subtracting a constant, but the mean is affected by adding or subtracting a constant. Right? So that particular example helps us come up with the rules for adding and subtracting a constant for random variables. Adding the same number a, which could be negative, to each value of a random variable adds a to the location and to the center. And remember, when I say adding, is add or subtract a constant. It does not change the shape. It does not change the spread. So adding or subtracting just doesn't affect the spread, like in chapter 2. Okay, going back to our El Dorado Community College example. At El Dorado Community College, the tuition is $50 per unit. Here is the probability distribution for T and a histogram of the, oh, I don't have a histogram, so don't worry about that. So, right, of the probability distribution. So there's the tuition, because we know it was $50 per credit, and that's 12 through 18 credits. We already determined this previously. So the mean of tuition is $732.50, and the standard deviation, the tuition, was $103. In addition to tuition charges, so here's the transformation. Each full-time student at El Dorado Community College is assessed student fees of $100 per semester. So lab fees, parking fees, whatever. If C is the overall cost for a randomly selected full-time student, then there is the equation. C is equal to $100 plus the tuition, because it's the lab or the student fees in addition to the tuition. Here is the probability distribution for C, no histogram again. What is the mean and standard deviation of the distribution? So the mean, C, is equal to the mean of the tuition plus the additional 100 in fees. So that would be 732.5 plus 100. So the mean of C is equal to $832.50. The standard deviation of C is unaffected by the adding of 100. So what all you do is, it is the standard deviation of the tuition. So the standard deviation of C is equal to $103. And the distribution would look like this. You're just adding $100 to the tuition. 800, 850, 900, 950, 1,000. And then the probabilities are still the same. All right, now putting all of this together, the rules for linear transformations on random variables, putting it all together. If y equals, so y is, here's your variable, so your random variable. So if capital Y is equal to a plus b times x, and x is capital letters, your random variable, is a linear transformation of the random variable x, then the probability distribution of y has the same shape as the probability distribution of x, the mean of y, because remember y is the transformed variable, is going to equal to a plus b times the mean of x. The standard deviation of y is going to be the absolute value of b times the standard deviation of x. Notice I did not put, oops. Okay, I notice I did not put the a there because adding or subtracting the constant doesn't do anything to the standard deviation. And then the variance of y is equal to b squared times the variance of x. And this is your original variance. We don't really work much with variance, though. We work with standard deviation. However, we will need it in the second and 6.2b. Okay, so let's do our last two examples. One brand of bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature X of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius, and that's for the variable X. Define a random variable Y to be the water temperature in degrees Fahrenheit. Recall that Fahrenheit is equal to 9/5 times X plus 32 when the dial is set on baby safe. So find the mean and standard deviation of Y. So the mean of Y is equal to 9/5 times the mean of X plus 32, because mean is affected by the scaling and adding or subtracting a constant. So that would be 9/5 times the mean of X was 34 plus 32. I did the math and I got the mean of Y is equal to 93.2 degrees Fahrenheit. The standard deviation of Y is equal to 9/5 times the standard deviation of X. But notice I did not put the plus 32. So the standard deviation of Y is equal to 9/5 times the standard deviation of X, which is 2. So that's 18/5 or 3.6 degrees Fahrenheit. All right, part B. And we needed part A to do part B. According to Babies R Us, the temperature of a baby's bath water should be between 90 degrees Fahrenheit and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby safe setting is used meets the Babies R Us recommendation. Show your work. Okay, so we want to find the probability that the temperature is between 90 and 100 degrees Fahrenheit. And so because we know this is a normal distribution, it tells us in the problem, we can use our normal CDF. We have 4 prompts. We have a lower bound, upper bound, mean, and standard deviation. Our lower bound, and if we were to draw this, our lower bound would be 90. Upper bound is 100. You could totally draw this where you put your mean 93.2 and then so on, but you don't need to. And then your mean is 93.2. So that's the mean of Y. And then your standard deviation of Y is 3.6. Do the second vars, and then that will get you to your normal CDF, and that'll give you 0.7835. And so that means the probability that the water temperature on a randomly selected day when the baby safe setting is used meets the baby's RS recommendation is 78.35%. So you can express it as a proportion or as a percent. Right. And last one. In a large introductory statistics class, the distribution of X equals raw scores on a test was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. So that's going to be y. So our equation there is y is equal to 4 times x plus 10. Define the variable y to be the scaled score of a randomly selected student from this class. Find the mean and standard deviation of y. So the mean of y is equal to 4 times the mean of x plus 10. And so that would be 4 times the mean of x was 17.2. I underlines all this stuff, plus 10. And so the mean of y, oops, I'm getting kind of sloppy here, is equal to 78.8. And now let's find the standard deviation of y. So the standard deviation of y is equal to 4 times the standard deviation of x, and not the plus 10. So there'd be 4 times, and I underlined that the standard deviation of x was 3.8, and that would be 15.2. What is the probability that a randomly selected student has a scaled test score of at least 90? So the probability that the scaled test score y is greater than or equal to 90 is going to equal, again, use your normal CDF. Please make sure you're practicing this. Of course, you get to do it on the homework, so that's going to be great. So 90 is going to be your lower bound, and your upper bound, just pick something big and don't pick like 100. Well, you definitely don't want to pick 100, and you just want to be far enough away, so pick 1,000. So lower bound, upper. So much writing. Never thought that mathematicians would have to write so much. The mean is 78.8. That's the mean of y. And our standard deviation was 15.2. But you have to identify these for getting full credit. You can't just write a bunch of numbers. That doesn't really help anybody who's grading it. Or if you make a mistake, I can't really go back and see what you did. And so that gives me 0.2306. So the probability that a randomly selected student's scale test score is at least 90 is 23.06%. And those are your notes for today. Have a great day, stat students.